Bom dia a todos. Vamos agora assistir a uma apresentação do professor Giorgio Cattaneo, ele é diretor do Instituto de Engenharia Biomédica, né, Biomedicina da Universidade de Stuttgart, na Alemanha. Ele vai fazer uma apresentação da experiência do trabalho que ele desenvolve lá, né? E esse é o início, nós esperamos, de um termo de cooperação, de uma relação onde possamos ter permuta de estudante, de professor, de trabalhos realizados em conjunto com esse instituto, né, para ver se a gente também cumpre algumas etapas, principalmente do que os nossos governos estão programando para o futuro, né? Nós temos agora, foi reativado o G6, é um programa do governo federal, né, de estímulo à indústria da saúde no Brasil, né, e se espera-se que as universidades possam trazer suas contribuições. Então, vamos iniciar. Professor Cattaneo, com você. Du hast die Worte jetzt.
Vielen Dank. Today at your university, now my microphone is starting working, I think. I don't know whether you heard the first words, but I repeat it shortly. I very appreciate to be here. I very appreciate this opportunity to give my talk in front of you today. So my presentation is about minimally invasive catheter-based technologies for cardiovascular interventions today. And I'm Giorgio Cattaneo. I'm professor and director of the Institute for Biomedical Engineering at the University of Stuttgart. I've been a professor there for the last three and a half years. Before I was in the industry for a longer time, working in the field of cardiovascular technologies. And I would like to give you a very short explanation about how I came to these topics, how I came to cardiovascular technologies. This is my background. I was born and I grew up in a city in the northern of Italy, Milan, which is very famous. Don't know whether it's very famous. The picture is small. Can we make, this is better, I think. They don't need to see me 2 times. So Milan is very famous because of the cathedral, the Duomo di Milano is called. And also for shopping, Milan is considered as a fashion city, so you can buy a lot of clothes and shoes there. But I've never been really familiar, interested in shopping or in fashion. I was more interested in techniques, and so I decided to go to the university in Milan, to the Politecnico di Milano, which is a school for engineering in Milan, and I decided to study mechanical engineering in the 90s. At that time, we didn't have the opportunity to study medical engineering. We didn't have this kind of course of degree program. So I studied mechanical engineering, but since I was not really interested in cars or in engines and so on, I decided to specialize in a very particular field, which was at that time quite new, which was called biomedical engineering. we managed, or we dealt with technique and biological system. The focus was the cardiovascular system in my courses 20-25 years ago. We learned in our courses how a technical system, a technical pump could reproduce our biological pump. So was it possible to reconstruct our heart? These are pictures taken from my lectures notes from that time. We learned how it is possible to replace our heart valve with a technical system. This is just a sphere which moves within a cage in two different positions according to the pressure gradient. During systole, when the heart beats, the sphere moves and the blood flows. And when the heart relaxes, the valve will close and provide the blood from flowing back to the heart. So it was one of the very first artificial valves I got familiar with. We learned how to treat occlusion of our coronary arteries, occlusion which prevent the blood from flowing to the tissue, using synthetic tubes, very small Teflon tubes connected to the artery to bring blood to the heart if an artery is occluded. So we learned how to deal with technical materials to replace biological, physiological function which were not working in our system. So all these systems were very innovative and very new from our perspective at the time, but had a very important limitation. All these techniques, all these kind of implants were very invasive. In order to bring these devices into the body, you need to open the chest, open the thorax, to stop the heart from beating and connect the heart and the circulatory system with an external machine, which is called heart-lung machine, which gets your blood and pump your blood, oxygenate the blood, and bring it back to the body while the heart is not working. And this is very invasive. This is very much stress, a kind of assault to the body, which was also associated to high mortality rate and also to very high complications. So what I didn't know at the time when I studied was that a kind of very, now it became small again, I don't know why. So a new technique had been developed some 10 years before, but at the time when I studied, it was probably not, it hadn't established itself, so I didn't have it in my course. But in the 80s, one physician, which is, whose name is Giulio Palmas, implanted for the first time a balloon expandable stent to treat a coronary artery. And this was the first procedure which was possible without stopping the heart from beating. It was possible to treat the heart while beating. And this was very important. So you didn't need any, excuse me, can you? So you didn't have this big stress for the body to bring the blood outside. This was what this guy, Giulio Palmas, is looking at, a very small device, a kind of metallic grid mounted on a balloon and connected to a catheter. And this works like that. So you have your body, you have a first step which is called navigation. In navigation, you put a very small tubes from the leg artery to the heart. And then you provide angiography. Angiography means you inject contrast agent within the vessel, and this contrast agent can be seen by X-ray. So it's possible to see that there is an occlusion here. The contrast agent is not flowing into the heart. This means there is a kind of narrowing of the artery, which prevents the blood from flowing to the heart. And what we do with the balloon expandable stent is to bring a balloon inside with this metal grid, expand the balloon with very high pressure to 10, 12 bar, and bring this metallic grid to the vessel, enlarging the vessel, providing the blood flow to the heart, and so ensuring the perfusion of our heart tissue and stabilizing the vessel. So today I would like to summarize the medical background of cardiovascular diseases. I would like to give you information about innovation in catheter-based intervention. I will go to some biological reactions which are very important with regard to complications which may occur, and then I would like to give you an insight into the work we are doing in our institute, because of course we are very interested in an exchange and in cooperation in the future. So let's start with the medical background. For those of you who are not studying medicine or don't have this kind of background, I will go very shortly to the function of our cardiovascular system, which consists of heart and the vessels, so the arteries, the capillaries, and the veins. And the function of our cardiovascular system is to transport blood to the tissue, and we call this kind of mechanism perfusion. This means we transport to the tissue energy, we transport nutrients and remove waste products from the tissue. The blood transports immune response, or cells for immune response and for tissue regeneration in case of inflammation or in case of injury, and is also responsible for temperature regulation. This means we produce heat and we need to transport this heat out of our body. This is something the blood also does. It's a very well-functioning system with a kind of performance that we could, as an engineer, if you look at the efficacy of this system of the heart, we would say performance is low. It has an efficacy of around 10%. It means 10% of the chemical energy coming to the heart is transferred to hydraulic energy. It's not a lot for a technical system. We would have a higher efficacy. But the performance is great with regard to other aspects. The heart is able to work over the whole life. No technical system is able to provide this kind of function for 70, 80, 90 years. The circulatory system is able to auto-regulate itself. If a tissue needs more blood, the vessel will open themselves, they will enlarge and bring more blood to the tissue. It's an automatic mechanism in our circulatory system. But probably the most fascinating of all the functions of our cardiovascular system is the ability to auto-repair itself. So if we have an injury, if we have a leakage in our system, the vessel will be able to repair themselves. No technical system is able to do something like that. And the mechanism which makes it possible to have a kind of auto-reparation, it's a physiological mechanism which is called hemostasis. In hemostasis, two different cells play a major role. The endothelial cells, which are the cells which cover the inner wall of the vessel, and the platelets, which are very small cells with diameter of around 2 microns, which flows into the bloodstream. When we have an injury, the line of endothelial cell on our wall will break, and the platelet, these cells floating into the bloodstream, will come in contact with the tissue behind the endothelial cell, which is called subendothelial tissue. And this contact between the platelet and the subendothelial tissue will lead to an activation of the platelet. And the platelet which become activated, they start producing a lot of biochemical reactions, producing new proteins and so on. Two very important proteins are thrombin and fibrinogen, which transform in fibrin. And all this biochemical mechanism will at the end produce a thrombus. And the thrombus is our plug. It stops the bleeding. It's a very important function. Otherwise, we would bleed very fast. This is not the last step of hemostasis. If it was like that, at the end we would be full with patches all over our circulatory system. So our circulatory system is also able to remove this thrombus and regenerate the tissue. And this is possible by means of macrophages, which are white blood cells, which migrate within the thrombus and activate some other reaction with contribution of smooth muscle cell in the vessel. And this biochemical reaction will lead to a reconstruction of the vessel and of the endothelial lines. At the end, the vessel is exactly like it was before the injury. And this is a process which occurs over the time in our body, not only in our skin, but also in our organs. We have always injury, and these injuries are repaired over and over in our life. This is an extremely complex mechanism because it involves so many cells, because it involves so many proteins in the blood. And probably exactly this complexity makes this process also very vulnerable, very sensitive. Many diseases brings to a misfunction of this kind of process in the interplay between endothelial cells and platelet. And this is a reason why cardiovascular diseases represent the fourth cause of mortality worldwide, because this mechanism doesn't always work. And this is also the basis for diseases like heart infarction and stroke. So underperfusion in the heart, underperfusion in the brain. What happens? The endothelial lines doesn't work as it should work because of inflammatory process, because of diet, because of inflammations, and so on. And some cells and some proteins migrate into the wall of the vessel, and the vessels start thickening. It develops a plaque, which is a region in our tissue full with fat cells, with lipids and inflammatory cells. And the vessel becomes smaller and smaller, more narrow and narrower. And this means that for the blood, it becomes more difficult to flow to the tissue. For the heart, it means more work to pump the blood into this narrowing. And this is a very gradual process. It's not very acute. So the patient or the person with this kind of disease will have some effort to go on the steps, to walk, and so on. But it's not an acute process. It can be treated. What's acute? It's what the blood produces. The blood is very sensitive with the platelet, and when it flows within this narrowing, the platelet will be subjected to very high velocity and shear stress. And this shear stress is also able to activate the platelets. And the platelets, after this narrowing, will circulate and stagnate in this region behind the narrowing, like in the river. In a riverbed which enlarge, you will have some stagnation and turbulence and so on. And these mechanisms leads to agglomeration of the platelet and the formation of a thrombus. And this is a very fast mechanism. While the stenosis, the narrowing, occurs over the years, over 10 years, 20 years, this formation of thrombus occurs in seconds. And this is what happens with heart infarct and stroke. Very, very sudden, very fast process, which have to be treated in a very acute setting. So now what have we experienced in innovation in all these years? What did I see in my time? After my study, I was working cardiovascular disease, and I saw how the technology evolved to make this kind of treatment of narrowed vessels better and better. So one of the main aspects of innovation was, of course, the miniaturization. This means the idea to make these implants smaller and smaller, to be able to be fast with very small catheter, to be very gentle in contact with the tissue, in order not to provoke big damages to the tissue while making this kind of treatment. So we wanted to be smaller and smaller, and this is a field of research I was working in development of this kind of device with very, very thin structure. This is a laser cut stent. It's cut from a tube. You have a metallic tube, you cut it, and at the end you have a grid. And this is an implant made of microwires which are braided to each other. And these kind of implants have been developed till a point where the structures have thickness of around 40, 50 microns. It's very, very small for us. It's also difficult to look at this kind of implant. And this miniaturization, this ability to making our technology, our material thinner and thinner, has made possible for us to bring these implants in very small catheter, which have diameter of less than 1 millimeter. So the smaller catheter now have diameter of 0.5, 0.4 to bring this implant to the vessel. And what happened with this kind of technology? So this is a part of miniaturization. At the other side, we developed the mechanics of this implant and made a step between balloon expandable, which is it's a very strong way to bring an implant, and self-expandable implant. In self-expandable implants are compressed within a catheter. They are not mounted on a balloon, so you don't have any balloon. You bring the implants into a catheter. If you pull back the catheter, the implant will expand by its own force. So it has a self-expandable mechanism. And then at the end, it will adhere to the vessel wall in a very gentle way. So they are smaller, and they are also more gentle. And this kind of combination of dimension and mechanics made it possible to bring the catheter, the implant, very high in very tortuous vessels, in very thin vessel within the brain, and open the door to very new application. And I would like to show you some of this application in the brain and some of this application in our region of our body. So this is an example of application in the brain. You see, it's a very nice video you can find also on YouTube. These are vessels within bringing the blood to our brain. This is a very small wire which penetrates a thrombus. This is a thrombus which forms into an artery in the brain and blocks the blood flow. This is a catheter. And as you can see, a very small implant is brought into the catheter at the side of the thrombus. Pulling back the catheter brings to an expansion, a self-expansion of the implant, which engages in the thrombus, creating a mechanical force to pull back the thrombus from the circulation and reopen the vessel wall. This is possible only if you work with very small dimension because of the size of the vessel in the brain and because of this very tortuous anatomy. Another example of operation in the brain which have been more and more performed over the time, over the last 10 or 15 years, is the treatment of aneurysm. Aneurysm are bulging of the vasculature. You can recognize it here. It's a kind of ball which forms on the vessel wall, which can bleed if the blood flows. You have a pressure in the aneurysm, and it can bleed, creating an hemorrhage in our brain. It's a very, very dangerous disease. The miniaturization gives us the possibility to build very, very small devices with micro wires which build a very fine mesh structure. And if you put this kind of structure within the vessel, you will interrupt the blood flow, prevent the bleeding or stop the bleeding, and create a thrombus within the aneurysm which completely occlude the aneurysm and prevent the bleeding over the time. So we use the mechanism of thrombus formation, of hemostasis, to repair our aneurysm and to prevent the bleeding from the aneurysm. Other applications in our part of the body were also possible or have become possible with self-expandable miniaturized device, like for example in the repair of the aortic valve. I showed you one of the very first devices. It was a sphere which moved in a cage, a very big stress for the blood. The new valves look like that, and they are made by a metallic frame which self-expand, integrated with biological tissue which is produced by the membrane of the cow, of the bovine membrane, pericardium it's called, decellularizing it, so removing biological components and integrating in the metallic frame. And this is a very nice video of a test performed in a model out of the body in a bovine, in a swine heart. This is a ventricle that you see here, and here you can see the catheter, and the pulling back of the catheter will bring to expansion of this kind of frame where the valve is mounted. You can see how the valve starts opening, and replaces completely the natural valve, which is squeezed on the side. So without stopping the heart, without connecting the heart to any heart-lung machine, we are able to put a new valve, an artificial valve, within our natural valve. And this is a method, this is a technique which is revolutionizing one of the big diseases we have in our heart, and this is a disease of heart valve. So you can see now how the valve open and close, and this is the other side. So this is the side of the valve looked at from the aorta. So we are working on integration. So the community of cardiovascular engineering is working on solution to integrate electronics into the implant. This is also a very big trend. The idea to bring electrodes in this very small device will give us in the future the possibility to monitor some signals from the body. And monitoring a signal of the body will increase the safety of the patients against complication. And one first device has already been introduced into the clinic, so in patient. In this device, a very small implant is placed within the brain, within a vessel, and the electrodes are able to detect signal from the brain. And the detection of the signal of the brain is used to control motoric function. And this is for people who cannot move their body. So for paraplegic patients. This is a very, very first level research project, but already in patients with very big potential for application in the future. Now, before I start speaking about our research in the Institute, I would like to give you another example. I think it's my last example about a new application made possible by miniaturization. And this is a support of the heart self. I showed you this very big artificial heart, so the technical heart replacing the complete heart. A lot of research has been made in trying to support the heart instead of replace it with a technical system. And these kind of pumps are also mounted on catheters, so they are called catheter-based blood pumps. The first of all these pumps were produced in the 90s and were also implanted on patients. As you can see here, we have a catheter and a rotor. This rotor is rotating with something about 20,000 rotations per minute, very, very fast, and pumps the blood from the ventricle. So it sucks the blood from the ventricle and pumps it into the aortic, decreasing the work needed from the heart to pump. So it alleviates the work of the heart before transplantation, or in order to give the heart time to rescue and recover its function. The problem of this first device was the shaft, which was rotating with a very high speed. And if you have a shaft and you bend it in the vessel and you start rotating, you will have alternating stress in the shaft, which is called fatigue. And this can bring to a break of the shaft. And this is what happened in patients. After some days, the shaft broke. And of course, if the shaft breaks, the rotor won't rotate anymore. And so some different solutions have been developed, and this is very interesting. This has been developed in the institute where I performed my PhD. I had also some works together with this kind of, or involved in this kind of technologies. In this pump, their shaft is not rotating because the motor is inside the pump self. So we don't need to bring the rotation. We bring the electricity. And the electricity will produce with this very small motor rotation of the rotor in the pump. Then we will have the blood sucked from the ventricle, flowing through the rotor, flowing at the side of the pump, and removing the heat produced by the motor. It's very interesting because the blood is a fluid that we need to pump, but at the same time is a coolant, so it's used to cool down the temperature of the pump. Otherwise, if the temperature increases, we might have any damage of cells within the blood. It's very promising technology, and it's really has been used more and more over the last 10, 15 years in supporting the heart before transplantation, also for recovery. So what's tomorrow? Tomorrow probably we will have pumps which will be even smaller than this pump, and the idea that some companies are following, are facing, is to produce this kind of pumps with self-expandable materials. This is in case a cage with a certain dimension. But if we get the rotor expanding after implantation, we can insert the pump using a smaller catheter, having the rotor expansion and then the force for pumping the blood into the vessel. Some companies are working on that. It's not inpatient, but it's, in my view, a promising technique also to miniaturize, to bring this pump in smaller system. And bringing them in smaller system will make the access to the body even faster for very emergency situation where you need small size to be very fast in accessing the heart, accessing the circulation. So different applications which have been possible by mechanics, by miniaturization, but also implementation, integration of electrical components, mechanical components in this kind of catheter-based device. And all these techniques can be used without opening of the thorax, without opening of the chest, without blocking the heart, without connecting the body with the heart-lung machine. They are minimally invasive, so the heart beats, and you can perform this procedure without major stress for the patient, which is a fantastic improvement we have had in the last 20 years. So there is still a problem. If we bring materials within our circulation, we still have a big stress. And this is what I want to show you in this next topic about biological reaction. A material placed within a vessel or within the heart means a tremendous impact for the physiological system. And this impact includes a mechanical mismatch. This means the stent made of metal, this implant made of metal, has a very different mechanical characteristic than the very soft tissue. So the mechanical stress will be very, very huge for the cells which experience this metallic part in contact with it. We have fluid dynamic alteration. So the blood is not programmed, is not conceived to flow in this kind of metallic grid. We will have turbulence, we will have some high shear stress. And then we have a biochemical stress. Metal is not projected to be within the body, or the body is not projected to be in contact with any metal. So we will have a kind of biochemical interaction. And these different factors will lead to a biological reaction. And it can be a good biological reaction, or it can be a bad biological reaction. At the end, we will have always a kind of platelet activation because of these factors and aggregation. We will have infiltration of macrophages, so white blood cells will infiltrate into the tissue. We will have release of inflammatory factors from the cells which are stressed under this condition of interaction with a metallic surface. So what does a biological environment does in this, while this interaction occurs? In the best case, this kind of inflammatory reaction will lead to tissue regeneration, the same that happens in hemostasis. The cells react and reconstruct tissue, and at the end we have endothelial cell covering the structure of our metallic grid and let the implant completely disappear from the circulation. At the end we have a normal vessel again. This is our very, very best case, and this is what we have, fortunately, in the most of the intervention. But it's a very dangerous game that we are playing, putting a metal in the vessel. This kind of inflammatory reaction which takes place can also produce such kind of mechanical stress, or kind of biochemical fluid dynamic states which induce an inflammatory reaction which overshoots in tissue regeneration. The cell starts producing more and more cells to hyperproliferate. This is the word that we use. and at the end grow over the channel within the vessel, recreating a new stenosis. We describe it as a restenosis. So we are trying to treat a stenosis. We produce a mechanical stress, and this mechanical stress produces a stenosis again. This is a restenosis. In order to prevent this kind of inflammatory process, we use in our device, in many of the stents implanted in the vessel, we use drug-eluting stents, or drug-eluting implants, which are implants with some drugs, which is released into the tissue to prevent any proliferation, any new building of tissue. And this is, from one side, good because the vessel doesn't narrow, but it prevents also the endothelial cell to grow across the structure, so we don't have any healing, we don't have any regeneration of tissue. And this means that these struts, this metallic grid, will be very inactive in the blood, and if the metallic grid stay inactive in the blood, we will have probably at a certain time, at a certain point, platelet activation and the thrombus formation again. And this is called in-stent thrombosis. So if we prevent the tissue to grow, we will probably have a thrombosis in the stent. So we want to prevent thrombosis, of course, because it's very acute and it could mean that the blood doesn't flow anymore. What do we do to prevent this thrombosis? We treat the patient with antiplatelet therapy, anticoagulants, so which are some drugs which reduce coagulation, which reduce hemostasis. And it's good for thrombus formation, but again, it's not good because we are stopping a physiological process. We need to stop bleeding in other parts of the body. So having these drugs in our body may mean that we have a bleeding in another part. So if we have the drugs to prevent the thrombus here, we might have a risk of bleeding in other parts. So we have many factors which interplay with each other, and this is difficult to deal with these different kind of problems at the same time, designing the implant, the coating, the drugs you use in such a kind of way that you get rid of all these problems, restenosis, thrombosis, and bleeding with a balance of all these factors. And sometimes it works. In the worst case, it doesn't work, and you will have one of these pathologies. So there are very strong risks related to implantation. And we have another problem. Our system, we are not machines, so it's very variable. We have different physiological parameters, different blood flow rate, we have different mechanics of vessel, we have different anatomies, we have also different biology, and so on. And the procedure might be different in a clinic or in the other clinic. And this variability, this big variability, makes very, very difficult to predict when an implant will work and when an implant won't work. And sometimes it happens, the complication occur, and we don't have any idea in which patient this complication will occur. We don't have any idea whether a patient will have an open vessel or a thrombus will at the end form in the vessel. It's so difficult to predict it. There are two ideas how to main radiation research, how to improve the biocompatibility to prevent, to reduce the risk of complication, thrombus formation, or reaction. Many research groups are working at. We have also worked at this kind of technologies. The first of all the first of these technologies refers to the bioabsorbable stents, which are implants which enlarge the vessel, but over the time degrades into the blood flow, so they disappear from the circulation. This is not an easy process because you have to control this process. You don't want the implant to disappear after 1 hour, but you don't want to have it for 5 years. So you have to adjust the parameters of your material in order to have a gradual and controlled disappearance of your implant within the blood. And these kind of systems have been introduced also in the clinics in the last year, but they are under development nowadays. And then we have another concept. This is about biofunctionalizing the stent with coating, with attract the endothelial cell. Will promote the proliferation of endothelial cell over the stent. So we have some coating which allows the endothelial cell or which promote the endothelial cell to move and also take some cells from the blood to cover they are called progenitor cells, so they are cells which are programmed to become endothelial cells, which at the end will cover the structure of the implant. And for example, I think in this case, completely occlude the aneurysm. So they are very important technologies we have which are very present, which are very strong in research in cardiovascular technologies. So, despite of all this improvement and all this idea how to improve the characteristics of the implant, the problems still remain. We have major complications, which are this kind of thrombi, which kind of reaction in the stent, for example, in an implant for the vessel, in the valve, in the artificial heart valve, or in the pump. All these pictures show you some thrombi which formed on the material and which prevent the function and can cause very serious complications. And this is the main motivation we have also in our institute to understand this kind of mechanisms and to improve them in the future. In this time working in this field, I learned mainly two lessons. And the first one is that despite or while we look at these implants and we see very small devices, miniaturized, which become smaller and smaller, this is only small for us, but for the biological system, these structures are huge. So if you consider this wire with 50 microns, it's much bigger than a cell, and it's also much stronger from the mechanics. We have to deal with the stress of the cell, and we have to work on this kind of interaction to make it more gentle for the tissue to tolerate. We have conducted an experiment, for example, together with the clinics on the devices that we had developed, laser cut and braided implants, and we looked at these implants after 3 days. It's not a normal time to remove an implant. Generally, you wait over months to see how the implant works, but we wanted to see what happened after 3 days. And after 3 days, we saw in the implants, in different kind of implant, between 60 and 100% of all the struts, so all the metallic elements of the structure which were cut in histology, between 60 and 100%, we had a thrombus. So when we put I cannot see into the vessel to see what happens with my implants as I can do with an in vitro test. I can just decide to explant the vessel after 2 months and see what happens, but I don't see the progress of diseases over the time. And then they are limited in number because of ethical reasons. So these are limitations. And for me, it's very important that in the future we fill this gap, we find better models for in vitro research will bring us closer to the biology of an animal test in order to postpone the use of animal only in a very late stage of research. So in the very last part of my presentation, I would like to give you some pictures, some ideas about what we do at our institute. The motivation is what I've showed to you, what I've learned also over the years in my work in developing these kind of devices. The complications or the motivation, there are still a lot of complications. If you consider 2 million of people are treated alone in the worldwide in the heart disease with coronary stent and other patients with our device, you can also imagine how many patients are affected by complication when a thrombus arises and so on. So it's a major, very big problem in dealing with this kind of device. The unpredictability is something that makes it very difficult to take decision about this kind of therapy. And the models that we have are to simplify the in vitro model before we go to the animal model. And these are the motivation for our work at the Institute. We are working at a new generation of models to investigate cardiovascular technologies in an in vitro environment before going to the animal. And we are working on new generation, or we are making research on new generation of biomaterials, on design and so on. We combine with our model to provide this solution in the future for this kind of implant technologies. We have 4 areas of work. We deal with minimally invasive technology with their manufacturing materials. We work with medical imaging and anatomical models. We have tissue engineering, so we bring the cell in our model, as I will show you later, and we have setups where we can investigate mechanics, biofluid dynamics, and transport process in our system. So let's start with implant manufacturing. We work together also with partners, also with companies which provide their implants for cooperations, for joint research, but we also have some technology we wanted to have in our institute to be able also to produce on our own, is something the students can also do. And one of the technologies that we have established is a braiding technology. So based on micro wires, which are designed, also students, and our scientists design implants, they model the mechanical force, the miniaturization, the delivering catheter as an engineering tool. And later on, we manufacture this kind of device. We have some manual tools for manual manufacture of this device. This is very nice because the students see how to work and how to fabricate with very small material on their own an implant. At the end, this is a manufacture of the implant. The implants are heated at the end to keep the form and then removed from the mandrel where they have been produced. And at the end, we have a self-expandable implant we can use in our model for different kind of research and different applications. And we are also starting a project for integrating electronics in this kind of implant. So we are working also with other 2 universities in a project which is funded by the German Research Foundation. And we are interested, and we believe the monitoring physiological parameters within the body will give us more possibility in the future to increase safety of patients and efficacy of the treatment. We personally believe that metal frames or metal structures are a good answer now, but it's not the only possibility. Metals and biological tissue has a big mismatch, as I showed before, because of very different mechanics. We believe the polymers will have a big role in the future. polymers is more similar to tissue, to human tissue, and match better the deformation, the mechanics, and so on. Probably more gentle for the tissue. Of course, it has a little less mechanical force, and this is exactly what we should in research investigate, how to use also material like polymers to treat this kind of disease. And this is an electronic system. In order to be able to work with polymers, we developed a machine, our own machine, which is an electrospinning machine, a machine able to produce small polymer wires, polymer threads, in a very well-oriented way. And this structure should be able in the future to allow for a proliferation of endothelial cells, for a biologization of the material within the vessel. And this is what we build. It's difficult to understand. Unfortunately, I don't have a video, but in this machine, some different parts move while the polymer is injected. And the polymer is injected under tension, under electrical tension. And with the distance of the polymers, with the tension, with the velocity, you are moving your substrate, you can change the way how these threads are formed, the geometry and the mechanical characteristic of these threads, polymer. And we are working with biocompatible polymer, which are also able to degrade in the biological system over the time. And I really believe that it's a very promising technology. As I told you before, we are working on anatomical model. We are provided from medical centers with anatomies, with medical imaging, and we reconstruct the vessel. This is called segmentation. We get the vessel out and we look at the disease, and then at the end we fabricate in a polymer lab based on silicone material, hydrogels, which are very similar to the human tissue. We reconstruct the different kind of vessel. For example, in this case, a carotid artery, aorta. The aorta, we are starting working with the heart, but also with other organs. And we implement this kind of work also in courses. So the students develop their own models, they produce their own model, and then they use this model for testing. So they get an implant, for example, from a company, and they learn how to develop the model and how to set the protocol of the test in order to investigate the implant technology. We perform in vitro testing. We have our own pulsatile system to reproduce a physiological curve. In this case, for example, we also reproduce a movement of the kidneys during inspiration, which also affects the mechanics of the vessel. We look at the implant within our material, our hydrogel. We have ultrasound, which allow us to look at the fluid dynamic into the vessel after implantation. And also here we implement this kind of test in the courses. Also here the students work with the catheter, develop their own implants, and they look at the different situations where the implant is working in and the effect of vessel movement to the implant function. This is an example. For example, we in a study where we characterize our model. So we look at different material, we look at the mechanical characteristics of the material, we adjust the hydrogels of the polymers in such a way that the mechanics of the tissue is well represented. And at the end, we use the model, for example, to implant a device. This is a device which was given by a company to us, and we placed on our model, and we let it beat. So with our pulsatile system, in order to look at the movement of the implant, to look at the structure change over the time, trying to find a correlation between implant design and way how it mechanically stresses the vessel. And at the end, we look also at the fluid dynamic to see the influence of this implant mechanics, implant geometry on fluid dynamic. We started with a fluid substitute, so we don't have blood in this kind of experiment. We want to see outside, but we are starting working also with normal blood, because the ultrasound gives us the possibility to look into the blood and also to visualize thrombus formation, which is something we want to focus on in the future. We are working with tissue engineering. This means we want to bring also cells into our model to understand the interaction of our implants with endothelial cells. So we are working with biological material, this kind with a vessel produced, so taken out of the heart, in this case of the pig. And we are working biologizing our hydrogels, our material. We build a bioreactor, so we have different channels, different hydrogel models, and we bring the cells inside. This is something we have developed and we are characterizing now. So we have starting now with cellularization of planar structure. This is a result of our work to change the material surface in order to have a good endothelialization. And now we are starting reproducing this endothelialization in our vessel model for a better understanding of the interplay of implantation and biological reaction. And we have also a very exotic project in this project, which is also funded by our local government. We are working on using plant structures, which have an advantage. They are very available, so it's much easier to have plants than animal tissue. They are very available. We are working on changing the structure of the plants, removing the structure of the plant. You can see here the change of the plants also in color after removing the cells. And then we have scaffolds. And these scaffolds made of cellulose are very good substrate to put cell inside. And now we are working on characterizing the mechanics of this kind of structure. And also the surface using electronic microscopy. And the step we are going now, we have already started, is to bring the cells in plant structure. So at the end, I hope it was a sufficient insight into the problems and into the work that we are doing in our institute. At the end, I would like to summarize what I've showed you today. The minimally invasive treatment which have been developing over the year are life-saving technology, but they are also associated with important risks. There are some trends, or there have been trends, with regard to the miniaturization of the system, to making it smaller and smaller over the time, and to biofunctionalize it in order to provide a better reconstruction of the vessel, better biological response also of the blood, and also to be able to put this system in very small catheter to access complex anatomies, like, for example, the anatomies of our brain. And this decrease of dimension and this biofunctionalization increase the safety of the devices in the patient, but still there are complications which are important in the clinical setting. So we have to work on this complication. We have to work on this kind of risk, producing better technologies and understanding them. And this is also, this is exactly our aim, to produce new knowledge that should be provided by new models of new generation, which gives us an insight about this complex interplay between the implant, between technology, and between our biological system, in order in the future to improve, to continue the improvement and development of minimally invasive technology. So I'm at the end. I thank you very much for your attention, and of course I'm very open for a discussion after my talk. Thank you a lot. And I would like to thank all these fantastic people building the team. We have built our team over the last 3 years, so it was a short time to build our activity. I'm very proud about the work these people have done, building new labs, producing new equipment, and setting the basis for research. Thank you a lot, my people. Thank you. This is a fantastic question over the timeline we need. I think it will be a very long way, I think we have to work on metallic implants, continue work on metallic implant, because so I believe that polymers will be the future. I believe that the metal will play a role in the next 20 years, of course. And the next step will be in research, in my perspective, to combine more and more these technologies. Combine metals, combine polymers, look at the requirements on your device. There are some kind of medical application where you need the force, where you need very strong implant which anchor to your tissue and stay over the time there. Metal has this kind of advantage to reduce its force, so the dimension is smaller. With polymer, you need other solution, you need other idea how to create the way, how to make it possible that implants stay at the place without to increase too much the dimension. Some biodegradable stains are in polymer, so we have made this kind of step for this kind of applications for bioresorbable polymer-based stain. The trade-off is that they are bigger, so you need more material to produce the force. And then you have, of course, to find the balance and to weigh up the advantage of using polymer, which are more gentle, which bioabsorb, and the disadvantage of needing more dimension. I think it's a fantastic research topic, and it's a big vision, but we cannot forget metals. Metals are the state of the art, and they have to be developed over the next year. I would like also to say, also as an intermediate step, the biologization of metal is very important. You can reduce the kind of stress your tissue has if you are able to biologize or to biofunctionalize your surface in order to trigger some kind of reaction and inhibit other reactions. So there are many intermediate states in this way.
And just one question, regarding the new directive that has nowadays in Europe for medical device. I know that it's been tougher than it used to be in order to clearance the device, and how this new criteria for clearance of device is impacting your research right now.
Also very, very, very good question, and probably I have to say at this point, I am at the university now, and I have this big advantage to be free to believe in vision and neglect probably the guidelines. But it's also not completely true, because of course we strongly work with the industry. It's important, so we need the innovation in the industries, because at the end the industry produces and develops this kind of device. So we need the industry with work on innovative product. And if the guidelines are very hard, there is a risk and there is a big fear in Europe that innovation will decrease. And I think politics has to work on this. Politics has to support innovation in spite of very hard guidance. So I'm not saying guidance has to be weaker. So it's okay to have good guidance, but you cannot start innovation because you say, well, it's too expensive to produce because the border, so the quality level you have to reach is so high, the clinical study you have to perform before bringing it in the clinic, before getting money, is so high that you stop doing innovation and producing. It cannot be the solution. It's a risk, but probably I'm optimistic, and I believe politics, researchers, company will find a kind of solution to continue with innovation. So I believe, and I would like to think of innovation again and again. Danke sehr, danke sehr. Danke. Danke. Wieder?